this is how it's going to be done, qualitative analysis, right? So I will be working out all on the board, and I'll be showing each and every concept on the board. You will have to note them down definitely. If you can't help, you have to note them down. So this qualitative analysis, right, so is a process that is done in chemical laboratories to identify anions, cations, and gases. Means it's basically anions, cations, and gases, right? So we will be first of all covering anions, and then we will move on to cations, how to test cations, and then finally we will move on to gases, right? How to test the gases, right? Okay, all right. So we are under anion analysis. Right? Once again, we are going into a subtopic, right? Anion analysis. Anion analysis, right? Okay. So under anion analysis, the first analysis that we are going to do is the halide analysis. Halide, identification of halides. Halide identification. These are the halides that we have to identify. Okay. So all right. So mostly we are going to, so fluorine F minus is negligible. We can't identify F minus, right? So it's not, we can't. It's not going to like, because it's like this, you know, when it comes to fluorine and the rest of the halides, they are two groups. Fluorine is one group. The other set of halides is another, like, group means, I mean, like, they behave separately. Like the behavioral pattern is completely different, right? So like fluorine behaves somewhat aggressively at some times, and then like these things, the other three halides, they behave somewhat different. So based on this qualitative analysis, right? So you can mainly target to identify the chlorine, bromine, and iodine, right? So these are the halides that we are going to see, right? So when I say halides, you need to like forget about fluorine in inorganics, right? So in inorganics for the time being, when it comes to qualitative analysis questions, mostly you can omit this fluorine, right? So omit this fluorine and consider, right? Okay. So the first thing is, right? First, under this halide identification, the first test that we are going to do is to identify halides, lead nitrate test. Silver nitrate test. So it's like this. First of all, like there might be a test tube. Let's consider there might be a which contains the halide, which contains the halide. So we don't know what halide is present. There is three options: either chlorine, Cl minus, Br minus, or I minus possible. First, what we do is, first of all, we add dilute HNO3. We'll see why these things are done and all. First of all, dilute HNO3 is added. Right. Dilute HNO3 is added. Next, what you add is this thing, silver nitrate. Then you add aqueous solution of silver nitrate, an aqueous solution of silver nitrate, aqueous solution of silver nitrate, right? Based, like when you do this, definitely if it is halides, you will observe precipitates. You will observe some precipitates. So based on the colors of these precipitates, you can decide the halide. You can decide the halide. If you are supposed to further verify the identification that you made, like okay, so I added silver nitrate, the precipitate formed, it formed a certain color, and then based on that color, I confirm that it is Cl minus. If I need to further confirm it or verify it, there are few more things that we could do. There are few more things that we could do, right? Okay, so before we move on to that, let's see what kind of observations are given. First of all, you add dilute HNO3. Along with that, you add silver nitrate to the solution where the halide is there. So if it is, like first of all, what we need to do is add silver nitrate. If Cl minus is there, it will show white color precipitate, AgCl. This is going to be a white color precipitate. White color precipitate. If it is Br minus, if it is Br minus, what will be the color? Yellow. Ag, this is going to be light yellow. If it is I minus, that forms is Ag. What is the color? Yellow color. Exactly. Yellow color. So, based on the color of the precipitate, you can decide the halides. Right? These things by heart, right? If you can't get the concept, by heart, can't it, right? Memorize. Now, there is a small issue. Light yellow, yellow, light yellow. People can find it somewhat difficult to distinguish what is light yellow and what is dark yellow. It depends, right? Based on what they see, right? So further, if there is a way to confirm the halides, it's better. So what we do for that is we add aqueous ammonia. Add ammonia to what? To the precipitates, right? To the precipitates. So I need to add the aqueous ammonia to the precipitates. When you add aqueous ammonia to AgCl precipitate, it dissolves. When you add aqueous ammonia to silver bromide precipitate, it doesn't dissolve. When you add when you add ammonia to AgI, doesn't dissolve. Now you can confirm Cl minus. So if they say in this way, okay, Cl minus is pretty confirmed, like once the color is given. Okay, white color precipitate, because the other two, they show yellow. Further, just you need to understand further, if it doesn't dissolve, if it doesn't dissolve, you can confirm that it's not this thing, it should be one of these two. So if you add concentrated ammonia, when you add concentrated ammonia to this precipitate instead of aqueous ammonia, instead of adding aqueous ammonia, you can add concentrated ammonia also. When you add concentrated ammonia, this dissolves. AgBr also dissolves in concentrated ammonia. This doesn't dissolve. AgI dissolves, right? And This dissolves when you heat this after addition of concentrated ammonia. It doesn't dissolve, right? Simply, when you add silver nitrate to I minus, it forms yellow color precipitate. When you add concentrated ammonia to that precipitate, it doesn't dissolve. But what happens is, when you after addition of this concentrated ammonia, it doesn't dissolve, right? So what happens is when you heat this to start to dissolve, heat this to start to dissolve, right? On heating, dissolve. Very important. Okay. So AgCl, when you add ammonia, it dissolves. If it dissolves, how is it going to dissolve? There should be a reaction, right? What kind of reaction is it? Like, if it dissolves, there should be a significant reaction shown. What happens is, this AgX, one of these X, right? X means either Cl, Br, or Y. This AgX reacts with ammonia to form Ag NH3 2 Ag NH3 2 complex. This is colorless. This is a complex. Correct? So this is why these things dissolves. Here, the concentration is not sufficient to form this complex. Right? In Cl minus AgCl, when you consider AgCl, it reacts with ammonia quickly and forms that compound Ag ammonia Cl. When it comes to AgBr, that doesn't form. Comes to AgI, that doesn't form. To form, you need to add concentrated ammonia. When you add concentrated ammonia, this definitely dissolves. It dissolves AgBr, but this doesn't dissolve still. Heat it. It will. Yeah. Okay. So why do we add dilute HNO3 first? In the solution, these are practicals, right? Solution, there might be CN, carbonate, sulfide, right? So these kind of ions might be there. Ions like, if ions like CN minus, carbonate, sulfide exists in the solution, they will react with whom? Ag plus that is being added. They will react with Ag plus that is being and will form precipitates. Correct? Not only these things, some others also. What happens when H plus is added? Carbonate converts into carbon dioxide and releases out. Sulfide converts into sulfur dioxide and releases out. Cn minus converts into some other compounds. Right? They will change their structure, which means like if not AgCN, precipitates might form. Ag carbon, silver carbonate precipitates, silver sulfides, precipitate. If this happens, when you add silver, the silver concentration in the solution will decrease due to formation of precipitates with them. Avoid that. First of all, you add a small amount of dilute HNO3, an acid, not dilute HNO3 always. You can add an acid, dilute acid. So summary is, because we can't discuss this slow, right? So there's a lot of things to discuss. So silver nitrate test to check one of these. Okay? So based on the color of the precipitate, when you add, first of all, you add dilute HNO3, and along with that, silver nitrate is added. So if it is Cl minus white precipitate, Br minus light yellow, this, yeah. So then, like, okay, these things are additional things. This is the reason. This is how these things dissolves, the formation of these complex, and this is the reason for addition of dilute HNO3 in the beginning. Let's go for the next test. That is lead nitrate test. Lead nitrate test. Once again, first of all, dilute HNO3 is added, and then to the test tube there is the halide, where the halide is there. You add lead nitrate aqueous. Add lead nitrate aqueous. Let's see what the observations are. Let's see what the observations are. When you add lead nitrate, PbCl2 precipitate will form.
A white color.
Exactly, white color. Br minus. What is the color? Right. White solid. PbI2. Yellow. Exactly. Yellow in color. Right? To further confirm, when you heat these precipitates, all of these precipitates dissolve. All of these precipitate dissolves, right? So when you heat the precipitate, this dissolves. Dissolves in aqueous medium, right? So what might be the color of the aqueous medium? Once again, that kind of a, not that, right? So a complex could form when heated and all, right? So we're not supposed to, even this is not supposed to learn, but still I just mentioned it in addition, right? So you are not required to analyze what the complex is formed, right? What kind of complex is formed. Simply, you need to understand the color the solution is formed when heating, right? When heating, right? Another, this thing is there to confirm, right? Another confirmation method is there. That is, this aqueous, like you heated this, right? You heated the precipitate. When you heated the precipitate, they dissolve. All of them forms a colorless aqueous solution. When you allow them to cool, so allow to cool. So when they are allowed to cool, right, they will form different kinds of precipitates. When they cool, they forms solids, precipitates. Okay? When you heat, things melt. Cool, they freeze, kind of. That is not exactly not what that is like. It's not going to melt and freeze, but still I'm saying, right? So the process. What's going to happen here is you will observe, right, white needle-like structures. White needle-like structures. So you are not required to know what that compounds are and then like these things in detail. Just the colors. Analytical means qualitatively you need to remember qualitatively based on the quality, the color, outer appearance. When this PbCl2 is heated, it dissolves. So when it is allowed to cool, it forms a white needle-like structures. But when lead bromide is heated, it dissolves. When you allow it to cool, right, it forms white color crystals. It forms white crystals. White crystals kind of precipitates are formed. And this one, TbI2, when you heat it, it will dissolve into colorless solution. When you further allow it to cool, it will form golden yellow solids. Golden yellow solids. Golden yellow solids. Right? So since I do not have space, I will mark it here, right? So the first one, if you consider needle-like structures. This is the solution. Needle-like structures will form. Needle-like structures will form. On the bottom, right? Solids, needle-like solids. This thing, right? White needle-like structures for what? Cl minus ions, right? Cl minus ions. So for Br minus crystals, what color crystals? White color crystals. Solution is there, white color crystals will form. For iodine, I minus, this kind of solids are formed. Right? So this is just joining. Like if you see a visual image, like you'll be able to remember these things. Right? So in that case, right, they are going to ask you to go and right? This. Okay. Once again, why do you add dilute HNO3? Anions, like they are present with lead 2 plus, they will form precipitates. If they form precipitates, the amount of lead 2 plus concentration in the medium is going to reduce. right? So for that, of course, you need to therefore dilute HNO3 is added to prevent this. All right. Carbonate sulfide. If they react with lead 2 plus, they will form precipitate. Lead carbonate, lead sulfide. Those are precipitates. If those precipitates form, the amount of lead 2 plus available to form precipitates with these ions will reduce. So we won't be able to do our experiment, like analyze this part properly. To avoid this, we add dilute HNO3 and remove these kind of unwanted anions. Right? Addition of H plus is not going to change. Addition of dilute H plus is not going to change anything in I minus, Br minus, or Cl minus. Right? But concentrated HNO3 if you added, concentrated H2SO4 if you added, things might change. Right? You need to remember with dilute H plus HNO3, no reaction. Right? Next test is Cl2 solution test. Cl2 solution test. Right? It's like this. So if you consider, if you first of all, what you need to do is you need to pass chlorine gas through. You need to mix chlorine gas. Like simply, you need to pass chlorine to an organic solution. Right? You need to pass Cl2 organic solution. For example, CHCl3, CCl4. This kind of organic solution. And then now it's not Cl2 aqueous, organic Cl. Cl2 is inorganic, right? So organic solution. Cl2 solution. Now you add this into the test tube. The halide. To the halide, this solution, right? After passing Cl2, the resulting solution sent to the halide. What will you observe? In this, what is there? Cl minus or Br minus or I minus. In this, what is there? Organic Cl. When Cl2 is added to a halide ion containing solution, like for example, let's assume bromine, Br minus ion is there. You put Cl2. Aqueous Br2. Displaces. It displaces, right? There's no gas form. There's gas formation is in very like small amount because of the volatile nature. A small gas is involved. That is true, but still, right? So actually, what happens is this solution will turn into two layers. No, I'm saying this. I'm saying inside either one of the halide is there, right? So not all, right? Either Cl minus or else Br minus or else I minus one. Either way, when the solution is added to this halide, turns into two layers. Organic layer and aqueous layer. Here halide was there, aqueous halide. This is organic. Organic and I can see this as organic, right? Assume Br minus was there. Sorry, I minus. Assume I minus was there. I minus aqueous was there. You add Cl2 gas. What happens? Cl2 gas means like initially Cl2 gas, right? Although it seems calm. What happens? Aqueous I2 this I2 when comes into contact with the organic layer, it shows a significant color. I2 in the presence of organic solution, organic solvent. What is the color? We have done this. I have shown you the color also.
Green color.
No green color was there in this kind. Iron green was there. It's for chlorine. It's not for violet. Right? If organic layer turns violet, if organic turns violet, then solution contains I. Similarly, if Br minus was there, when you add Cl2 gas, what happens? If organic layer exactly organic layer turns orange, then solution contains Br minus. What if the solution contains Cl minus? Will it show a significant change? There'll be no significant change observed, right? Already Cl2 is not going to displace. No displacement reaction. So no. So based on this, you're going to say you're going to say what? If this kind of an experiment is done, and if no color is changed, no significant color changes, then the solution contains. That's wrong. That is wrong. From this experiment, what you can decide is whether it is I minus or Br minus only. You can't decide whether Cl minus is there or not, right? You can't decide whether Cl minus there or not, because if there's no Cl minus also, it will not show a color change. So does that confirm that there's Cl minus exists? So from this experiment, like if it doesn't show a color change, if no color change in organic layer, what can be confirmed is that there is no Br minus or I minus ions. Because if either one of them were there, the color change would be shown. If no color change is shown, what we can confirm is only that there is no Br minus and I minus. No color change in organic layer confirms absence of Br minus and I minus. right? So to confirm the presence of Cl minus, what should you do? To check Cl minus, then what could you do? What you could do is you will have to do either lead nitrate test or silver nitrate test. Very simple. Right? Okay. To check Cl minus, you should do either lead nitrate or this thing, right? Okay. Right. One more important thing is, if both I minus and Br minus were present, if both I minus and Br minus were present, then what happens is the organic layer first turns brown, not brown, violet. First turns violet and then turns brown color. Purple and then turns brown and then turns brown. Right? So if both were there, this is what's going to happen. Right? This is what's going to happen. Right. Okay. They don't go to think, okay, what might be the reaction happening, and then simply just this is just an additional thing. Right? Additional. Fourth test is, right? Fourth test is concentrated H2SO4 test. Still we are under what subtopic? Identification of halides. And identification of halides. Right. So for a halide ion solution, right? For a halide ion solution, right? For a halide ion solution, when you pass or when you add some amount of concentrated H2SO4, right? So obviously, when you add these things, you will have to use this kind of a procedure, right? To add, because straight away if concentrated H2SO4 falls onto this thing, it might things might get worse, right? What you do is like you add concentrated H2SO4 solution. What happens is after adding concentrated H2SO4 solution, if you heat it, you will have to heat, right? If you do not heat, this doesn't happen. You need to heat the solution. If you heat this halide solution, what you might observe is evolution of certain gases. Evolution of certain gases, due to evolution of certain colored gases. Based on evolution of gases, we can't confirm the presence of certain ions. You need to observe properly. It should have a certain color. So, due to evolution of some colored gases, we can confirm the presence of the ions. Let's see if the halide present, if iodine was present as this halide, what happens? When iodine exists, what happens is I minus aqueous. For that, you need to add concentrated H2SO4. Actually, what happens is concentrated H2SO4 means, right, sulfur dioxide. Then concentrated H2SO4 means SO4 2 minus. SO4 2 minus. So SO4 2 minus can reduce to this acts. If this is reducing, this acts as a oxidizer. So it oxidizes I minus to I2, right? So this is going to be the gas. When you, right, you know, these things are volatile, right? Kind of volatile. They have the volatile nature. The gas will evolve sulfur dioxide gas and Br2, sorry, SO2 gas. SO2 gas is halides. We can't identify SO2, like based on SO2, we can't identify the ion present. But Br2 gas, I2 gas is what color? Purple. Purple color gas. Gas evolves, right? I will balance this because like H plus H2, right? I will balance this y minus H balance, right? So for a the halide containing is I minus, when you add concentrated H2SO4, you can observe and you will have to heat. If you do not heat, this will not take place because the oxidizing strength of H2SO4 is not sufficient. Oxidizing strength of H2SO4 is not very strong. H2SO4 is not very strong oxidizing agent. So we can use a strong oxidizing agent. And yes, obviously we can use, but these are practical things. So when Br minus exists, Br minus equals concentrated H2SO4 turns into sulfur dioxide, Br2 gas, exactly. Reddish, brown, sorry, gas, reddish, brown, gas evolves. Right. When Cl minus ion is present, right, what happens is a colorless gas evolves. It's not Cl gas, Cl2 gas. It's not Cl2 gas, right? Hope you understand what I say, right? Cl, when Cl minus exists, and when you add concentrated H2SO4, what happens is this concentrated H2SO4, the H plus from concentrated H2SO4 reacts with Cl minus and evolves HCl gas. Evolves a colorless gas. So then how do you identify based on a colorless gas? There's plenty of colorless gases, right? What is the test to identify HCl gas? That the gas that evolves is HCl, it seems. So we can come to a conclusion that the ion that was present is Cl minus, because from where can Cl come if there was no Cl minus? From where can HCl form if there was no Cl minus? So take a glass rod, dip it in HCl, concentrated HCl, and place it over ammonia, white fuel will form, right? So do the reverse now. Yes, take a rod, the glass rod, dip it in ammonia solution, place it over this gas. If a white fume is formed, we can confirm that the gas is HCl. That confirms the ion is Cl minus. Glass rod dip ammonia solution. HCl exposed for it, like this HCl gas exposed to a glass rod dipped in ammonia solution will form a white fume. Ammonium chloride. White fume. This confirms the presence of, okay, these things should be heated, right? So I mean, here, for this to take place, we need to heat it. This is. Right. So now Cl minus can also in this way be confirmed, right? Right. So why did Cl minus oxidize? These two oxidized to Br2 and I2. So then why can't Cl minus oxidize? That is, the oxidizing strength of H2SO4 is not sufficient to oxidize this guy, Cl minus. It's a highly reactive. What you said is true, but it should be mentioned in as the note. Right? The oxidizing strength of H2SO4 is not sufficient. It's not sufficient to oxidize Cl minus. So in that case, what you can do is you can use a stronger oxidizing agent. You can use a stronger oxidizing agent. So what you can use is instead of H2SO4, MnO2 in acidic medium can be used. In that case, what happens? When you use MnO2, the relative oxidizing power of MnO2 is higher than H2SO4, right? So simply I minus, Br minus, Cl minus, all these will get oxidized. So that is it for this Cl2 concentrated H2SO4 test. That's it for halides. We just have four tests, right? 4 tests.